Meta-analysis sits at the very top of the evidence pyramid. When available, it is undeniably the most reliable information about any given topic. Imagine you're a doctor and you genuinely have a patient's life in your hands, and you look for a solution in a medical textbook or in, a medical journal. What you find is, according to a study, drug A saved lives, but another study says that there is no benefit to drug A. So when that time comes, who do you trust? And this is not just a headache for students. It is a crisis for medicine, because most individual studies simply lack the power to provide definitive answers to questions that anguish us about medical care all the time. Or even if they can provide some answer, it's not the answer that we want because it lacks statistical power. That is where meta-analysis comes in. In this type of study, we combine all the scientific literature regarding a specific topic. First, we make a search strategy, and then we download every single study about that search strategy from several databases like PubMed, Embase, Web of Science, or others. After that, we do the screening process, meaning that we apply inclusion and exclusion criteria for every single study that we downloaded, which sometimes it's in the thousands. This meta-analysis, for instance, started with 3,969 results, but only 15 actually met all the inclusion criteria. That means that the people who wrote this article discarded more than 3,900 studies. They evaluated all of them, and they concluded that they were not supposed to be a part of this specific research. Now we get those 15 studies, or whichever number we're looking for, and we get all the numbers, all the data, and we just write them down in an Excel spreadsheet or Google Sheets or whatever. But basically, we gather all the data. After that, we get this data into softwares like Revman, R, Stata, and essentially those programs, they act as highly powerful calculators, and they create what it's called a forest plot. And the forest plot gives the overall answer to that specific question. So theoretically, if a person has a question if drug A is better than drug B, or if drug A is better than placebo, and that person read not one, not some, but all the statistical evidence about that, all the studies in all of these, databases that we were looking for, like Embase, PubMed, Web of Science, and many more. If that person could read all of those studies and, perfectly calculate the math in their head, assuming they could memorize all that data and come to the correct conclusions about that data, they would reach the exact same conclusions that we reached by doing a systematic review and meta-analysis. Using that forest plot from before that, I'm gonna make like an example now. This is all-cause mortality for patients with heart failure who take SGLT2 inhibitors compared to placebo. If I read all of those papers and could do all the math in my head, I would get to that conclusion, which is that they do reduce all-cause mortality, which is represented in that forest plot by that diamond sitting on the lower part of the screen, which shows that the overall hazard ratio is 0.86, which means it's lower than 1, which means that it reduces the overall effect that we're looking for, which means that it reduces all-cause mortality with the drug. If I didn't have this meta-analysis, I would have to read all of those papers to kind of understand what they were talking about. And even if I read all of those papers, I wouldn't have such precise measurements and mathematics in my head. And that's what meta-analysis is useful for, aggregating data and presenting to us in a very digestible format, which is the forest plot. So that's it. I hope you now understand what is a meta-analysis. Subscribe for more content like this one. And if you want to understand yourself how to perform a systematic review and meta-analysis, click the first link in the description. That's it from me, guys. Bye-bye. Till next video.